Hello, I'm Ryan Baker and this is Big Day in Education. Welcome to the third video of the third week of our class on feature engineering, one of the most important topics and least studied topics in all of Big Day in Education. Up until this point in the class, we've talked about building and validating prediction models, including behavior detectors. Models that infer a predicted variable from predictor variables. A couple lectures ago, we went into a little more detail about where the predicted variable can come from. But where do the predictor variables come from? Do they fall out of the sky? It's raining data, the data deluge. Do they come from the Office for Predictor Variables in Washington, D.C.? Man, I wish that office existed. So in fact, they come from feature engineering, which is the art of creating predictor variables. This is a major topic in its own right. Why is it important? Feature engineering is the least well-studied part of the process of developing prediction models, but it's arguably the most important part. Your model will never be any good if your features, your predictors, aren't very good. And its importance runs straight up against the fact that right now it's an art. It's human-driven design rather than being a clear process which you can just follow from start to end with no ability. Right now it still involves lore to a large degree rather than well-known and validated principles. We need to do better. It's hard. The big idea is how can we take the voluminous, ill-formed, and yet underspecified data that we now have in education and shape it into a reasonable set of variables in an efficient, effective, and predictive way. It's a process in its own right. You brainstorm features. You decide what features to create. You create the features. You study the impact of the features on the model goodness. Then you iterate on the features if useful, and then you go back to creating more features or brainstorming more features until you feel like you're done. Brainstorming features can be more or less formal. IDEO, which is one of the nation's leading design firms, has some tips for brainstorming. Defer judgment, encourage wild ideas. I like wild ideas. Build on the ideas of others. Stay focused on the topic. Have one conversation at a time. Don't split into lots of groups doing lots of stuff. Be visual and go for quantity at first rather than quality. I like quantity. I want to point something out. Building on the ideas of others doesn't just have to be people nearby. There's a huge literature out there of features that people have tried and what's worked or failed to work for a range of problems. Read papers from researchers working on similar problems and see what you can use. On hard projects, my research group often meets as a team over pizza and beer to brainstorm. On easier projects, sometimes one person will brainstorm solo and then discuss their features with another person who will offer further suggestions. Deciding what features to create, well, there's never infinite time. You have to decide because you can't make everything. And there's a trade-off between the effort needed to create a feature and how likely it is to be useful. Sometimes the best you can do for how likely it is to be useful is look at whether similar features have been useful for similar problems and use your best intuition. It's worth biasing in favor of features that are different than anything else you've ever tried before because it explores a different part of the space. There are a lot of approaches to creating features, however there's two primary ones. The first is tools like Excel, which are visual and as such are really good for prototyping features. You might not want to do it for a dataset with 15 million data points, but there's nothing that can be beat for actually just taking a small part of your data and trying to understand that to create features. The other end of the extreme is distillation code, the scalable solution, obviously, but it's harder to check yourself or to explore with it. My lab often starts with Excel to prototype and to understand what we're doing, and then builds distiller code to replicate what we built in Excel at scale. Excel's got a lot of useful tools for this, including pivot tables, which are great for aggregating data and getting the average, min, max, and standard deviation. VLOOKUP, which is great for translating from aggregations, student-level data for instance, back to action-level or clip-level data. So an example might be, how much faster is the current student action than the average student attempt? Sorry for the typo. How much faster is the current student action than the average student attempt on the current skill? So let's take a look at how you can do that. So we have a student, we have a skill, and we have a time. So we've got a bunch of different students, a bunch of skills, a bunch of time. So we first create a pivot table from all the data. We go to the Insert and click Pivot Table. And then we click OK. Often it'll come up with the right thing by default, but check to see if it's got the right variable range. Then we create a pivot table. So in this case, we're going to put as row labels the skill and as values the time. And you'll note that we're going to do both the average and the standard deviation of time. And you can see when we right-click on values, we get this value field settings option. We then get a set of variables. So for each row, for each skill in this case, we get an average time and a standard deviation of time, which we then select all of and paste special values, and click down below and copy out the data. Now we have two copies of our data, one in the pivot table, one outside. This is important because you can't and probably don't want to do a VLOOKUP on a pivot table itself. Then we go back to the original spreadsheet and we do a VLOOKUP. Let's talk about this VLOOKUP here. I know I'm kind of racing through this. My idea here is you'll be able to come back and look at this and then maybe see what you can do with this to be able to learn this on your own to some degree. So you VLOOKUP and you're trying to find the skill in that table of skills. And you have that table of all of the skills, their average and their standard deviation. You take the second thing and you put false. Last thing in VLOOKUP should always be false. There's more about that, but for every practical intent and purpose of what you'd be doing, false is what you want there. You then create the standard deviation, and that's the exact same thing, except we're looking at the third column of that table back there rather than the first one. And finally, you create unitized time by taking the current time minus the average time for the skill, divided by the standard deviation. And this gives you how much faster or slower the current student action is than the average time for this skill. So for some further resources about how to use Excel, here are a few I like. Go check this out on the lecture slides. Definitely worth looking at these. Other useful things you can do in Excel, there's actually a bunch of them. Count so far. You can create a count of how many times the thing has been seen so far in a student. Counts over the last n actions. How many times has the student done something like ask for help in the last 5 or 3 actions? Differentiating first attempts from subsequent attempts. Getting ratios between events of interest. And cutoff-based features. That's an if statement and a greater than less than. There isn't time to go through all these in great detail right now, but this is a powerful tool, and we'll look at this in the assignment. Another important step in feature engineering is feature iteration. Sometimes when a feature looks like it might be good, it's worth iterating on that feature, trying close variants to see if they do better. For example, let's say you have a feature, slow actions after hints, and you define slow action as an action taking over 20 seconds. It's plausible, but what if 30 seconds is the better cutoff? What if 30-second actions or longer after hints actually are a better prediction of student learning because these hints take 30 seconds to read and think through? There are a bunch of ways to accomplish this. There are a bunch of ways to test whether there's some better feature than what you've got. You could do it by hand. You could try 20, then 30, then 40, then 50, and try a bunch of stuff. You could do this programmatically. You could use Java or MATLAB or some other tool to try systematically all the options. 10 seconds, 11 seconds, 12 seconds, 13 seconds. My group has done this for some problems. Or you could use the Excel equation solver, which is a kind of neat tool that can do this. Now another key aspect is that the details of features matter. For example, the same feature can have a different impact depending on its context. Take this example from Baker et al. 2015. We can take the simple feature of, has the student opened their online textbook? Seems very straightforward. But in fact, whether a student has opened their e-textbook predicts whether they fail their course, but with totally different precision and recall on the first day of class versus the 7th day of class. Same feature, just 6 days different when we look at it, but in one case, the first day of class, it catches almost everybody who won't pass the course, who will fail, but it also catches a lot of people who will pass the course. On the 7th day, it no longer captures everybody who's gonna fail, but everybody it catches is probably gonna fail just about. So, same feature, just 6 days later, totally different semantics. Here's some tutorials for the Excel equation solver. One tip that you might find useful. For recent versions of the Excel equation solver, it actually doesn't do too good a job of searching the space compared to the earlier versions. Multi-start option is something you can use to avoid local minima that can sometimes block the solver from even getting started. I'd like to share a few more thoughts on feature engineering. First, does feature engineering overfit? Well, it can. Which is why it's useful to remember. The true test of a model is whether it works on entirely unseen data. If you iterate on your features a lot and you're using cross-validated goodness the whole time, then the cross-validated goodness will not be the true test of your model. The true test of your model will be either a held-out dataset or a newly collected dataset later on. One other thought on feature engineering. Your features come from somewhere. You can take a standard set of variables or pre-existing variables, and there's no question that's faster than engineering things. But thinking about your variables is likely to lead to better models. So in the next lecture, we're going to talk about the opposite of feature engineering, automated feature generation and selection. So I look forward to seeing you next time. I'm Ryan Baker. This is Big Day in Education. Thank you very much.